Arizona State University. She's going to tell us some computations on parameterized surfaces with Chebfun.
Yeah. All right, so like you said, my name is Courtney, and I'm just going to be talking about some of the cool applications that you can do with the Chebfun and Chebfun2 programs in MATLAB. So, the introduction, what is Chebfun, you might ask? So, the Chebfun software is just a collection of algorithms used in MATLAB. It's just an extension of MATLAB. So, Chebfun is based on the mathematical fact that smooth functions can be represented by Chebyshev polynomials. So, Chebfun is just on the interval from A to B, so it's just x. And then Chebfun2 builds off of Chebfun, so it's x and y. So it's from A to B by C to D, if that makes sense. And then the Chebfun2v object is just a vector composed of Chebfun or Chebfun2 objects. So here's an example of what a Chebfun looks like. So this is just cosine of 4x from 0 to 2 pi, where x goes from 0 to 2 pi. So you can see that here we have I made it show the Chebyshev points. So they're very collected towards the ends, and then it gets more spaced out towards the middle, and then back being closer together towards the ends. And then here, the Chebfun object in MATLAB, this is the output of it. So it's a polynomial of degree 38. So, and then here is an example of what Chebfun2 may look like on x and y. So it's pretty useful for surface modeling in MATLAB. And then you can also use it, you can use it on parametric surfaces. So u and v can be declared as Chebfun2 objects, and then you can make functions x, y, and z of u and v, and do computations that way in MATLAB. So that's what that looks like. And then one of the things I want to try out is see how you can maybe model trajectories and flows in 3 dimensions using Chebfun. So you can write r and theta for a torus, for example, as Chebfun objects, and then you can make f vector of those Chebfun objects. So it's pretty interesting. We're going to check this out over the torus. So if you're given a velocity field on a surface, you can use chain rule to find the path. So we're going to use least squares and then find dr d theta, or dr dt and d theta dt. And then you can use various computational methods to find the actual path. But you can plot that vector field you found in r theta space, and then using Chebfun, you can plot it onto the torus surface. So you can see the string function, and then the vectors follow the string function there. And then you can use like Runge-Kutta to estimate the path of the grid of particles. So that looks like. And then you can also map it onto the surface of the torus, which is kind of cool. It looks like little ants on a donut. And then you can also use Chebfun, Chebfun2, and Chebfun2v for computing curvature, or estimating curvature of a surface. So if you have a 2D surface in 3D space, and you want to find the curvature of that point, you have the point here, and then you have your normal vector, and then your planes of principal curvature, usually denoted kappa 1, kappa 2. And you can use kappa 1, kappa 2 to find the mean and Gaussian curvatures of a surface. So h is mean curvature, and that's what the equation looks like, where E, F, G are coefficients of the first fundamental form of the surface, and L, M, and N are coefficients of the second fundamental form. So mean curvature is just the mean of those two principal curvatures, and then Gaussian curvature is the product of those two principal curvatures. And then just a side note, you can find the first fundamental form coefficients by taking the dot product of the partial derivatives of the surface, and then you can find the second fundamental form by taking the dot product of the second partial derivatives and the normal vector. So this is where Chebfun2v becomes pretty useful. So in MATLAB, it's all numerics based. So usually it's pretty hard to approximate second derivatives with just a cloud of points. So if you have a cloud of points for a sphere and then you want to estimate the curvature of it, you can run a series of nested for loops to find your derivatives. And you get this discontinuity towards the ends. So my goal was just to improve the accuracy of that. So here is my implementation using Chebfun2. The reason why it is really, really convenient is because it's so easy to find the derivatives with this program because it has methods already written in. So you find your first and second derivatives here, and then these are the first fundamental form coefficients, and then you get your normal vector here, and then that way you can just use the methods and find the second fundamental form coefficients. And here, these are just the equations you saw earlier. This is Gaussian curvature, and then mean curvature. So you can run these in MATLAB and see their accuracy. So here is just an example. A sphere is a good way to test this out at first because it has constant curvature. So if the radius of the sphere is 1, its curvature should be 1. So here's just the instantiation of that in Chebfun2v. So here I run the program, and then I just want to test it out at a point here, and then you can see it's 0.999999 all the way out to 13th and 14th decimal place for both of them. So it's pretty accurate. And then you can also test it on surfaces with non-constant curvature. So I did monkey saddle here. So there's the parametrized version of it for Chebfun2v. And then I can graph the Gaussian and mean curvatures here, and then I thought it'd be cool to plot these and color the monkey saddle with the curvatures. So that's pretty cool. And then I also want to do it with the torus because it has some nice properties. So there's the instantiation there. And then one of its properties is that the Gaussian and mean curvatures are just negatives of each other, which you can see that here. And then again, they're mapped onto the surface. And then I also wanted to further this is my future avenues of research, into mean curvature flow. It's an example of a geometric flow of a surface, and it can be used to model things like droplets of oil and water, soap films, etc. So we can attempt to do this with Euler's method. So you have the new surface equals or old surface plus the change in the curvature with respect to time times the normal vector. So it should be, theoretically, if you were to have a sphere and you're going to do the mean curvature flow of that sphere, it should shrink to the center point. Or if you were to have a cylinder, it should shrink to its center vertex, or line. So I have a video of that just to see what it kind of looks like, but here you can tell that you start to get a discontinuity over time right about there. I'll run it again. Oh, it's running again. Right there. I don't know if you can see that or not. Let me see if I can pause it as it's going. There we go. So this is just due to the fact that we need to just fix some things using Chebfun because it does deal, this is a periodic thing. So we have to fix up the boundaries there at 0 and 2 pi. And hopefully we can improve that and then have some more fun Chebfun with mean curvature flows. So I wanted to acknowledge my research advisor, Dr. Plate, and then Dr. Kostelich and Dr. Kowski for helping me out, and then the National Science Foundation for funding the research, and then the Chebfun team for writing the codes.